Good, yes. So as the title says, I want to talk a bit about what we mostly do in my group, so-called learned reconstruction methods, and how we combine classic reconstructions and a data-driven regime. So this is pretty general in this presentation. So yeah, let's just jump right in with a motivational example. So here we actually see in MR a magnetic resonance image of a beating heart. So what we do in an MR scanner is we sample the Fourier space in principle. So we have K-space data and we can reconstruct with an inverse Fourier transform. To get such a nice image here on the right, we actually need to sample this pretty densely. So it takes a bit of time, well, not super long, but about 10 seconds. And in these 10 seconds, we need to eliminate outer movements. So actually what you see here on the side is your breast cage. So what we need to eliminate in these 10 seconds is the breathing motion to get this image or video of the heart. So what you would need to do is, of course, hold your breath. And when you do that with small children, you rarely can tell them to just stop breathing. So there's a need for real-time imaging, specifically in pediatric care. If we now do real-time imaging, so instead of having a full scan, okay, I think it's slowly loading. My presentation isn't going. Then, well, anyways, if we undersample, I just keep talking and hope my presentation is catching up. Yes, okay, I think we're there. Good, okay. So if we undersample, we only have a few lines in the so-called K-space, and if we use the FFT to reconstruct, we get this here in the middle, heavily undersampled data. So one of our early works actually, and now almost 6 years ago or 7 years ago when we started this, we just applied a convolutional network here to clean this up. And this gave us amazing results. So we were really able, by just training a CNN as a so-called post-processor to clean up this image, we got really nice reconstructions of this heart, which were clinically actually better than any classical reconstructions to deduce any markers from it. So it was pretty fast and actually very simple to train because you only needed these two samples, so one undersampled and one ground truth data. And you could generate these very easily if you have a large data set of scans, which luckily we had. In fact, that was in London, so we had a data set of the last 20 years. So that was pretty useful. Not everyone does have that though. So what happens if we only have a few samples? And ideally, we need to be very careful how to sample. So there's a bit of work actually going into this to design this problem. But the biggest problem for us mathematicians is that we do not get any guarantees on what we do. This is just the post-processing. So it just cleans up the image. Okay. So why do we need machine learning? I think it has become pretty clear in the last years that first of all, the image quality in our choice of imaging modality depends very much on the acquisition time, the signal strength. For instance, specifically, if we use X-rays, we would like to use a lower dose, then we get noisier images, and as we just saw on patient movements. Traditionally, we have used classic mathematical techniques for this to compensate for these factors, but many techniques tend to be slow, even though they are effective. And they can also be, computationally expensive and also very involved to solve. So we could improve this, as we just saw, by using data and data-driven methods. But what we want to do is we want to combine our data-driven and model-based regime by including mathematical and physics knowledge into the learning task and design algorithms based on classical reconstructions by basically intertwining the model-based components with the data-driven methods. So how would we do this? Let's have a look at first the classical reconstructions. So in a classical reconstruction, we first obtain from our data what we see here on the bottom. So this is actually from photoacoustic tomography. So this is basically pressure measurements on the boundary. We obtain an initial guess. So this could be filtered back projection, or in this case, time reversal. So we get some initial guess that might not be perfect. Then we compute an update, or basically by comparing our measurements with or the reconstruction of our measurements. So by here, we just evaluate the data fidelity, or in fact, we compute the gradient of it. So the gradient would tell us in which direction would we need to improve our reconstruction. That's pretty useful information. So then we have now these two, we combine them by some analytical update rule, for instance, by using a proximal gradient descent scheme. And then we keep repeating this many, many times until we have some convergence criteria reached. And at the end, we do get usually very nice images. Okay, so how could we now use deep learning in this framework? So let's give them some training data. So now we have training data, and instead of now handcrafting some update rules, what we want to do is we take this training data here and train a neural network, or in fact, in this case, multiple neural networks that now here replace, in fact, if we go back to the previous algorithm, replace our update rule. So the analytical update rule is now replaced by this neural network. So the idea here is that the neural network learns a more efficient update but exactly using the same information as the analytical update rule. And in fact, because it was replacing the proximal operator, which includes the regularization, the idea is also that the neural network can learn from the training data, the prior or the regularizer in some sense. We see in a few moments that it's not that easy in a strict mathematical sense. And then, because we also want to be more efficient, we give the algorithm a fixed budget. So in other words, we only want to have n iterations, where n is usually low, something like 5 or 10 iterations. And then we repeat this again for these amount of iterations, and we usually get even nicer reconstructions, which is quite amazing. Okay. So this is what we understand as learned image reconstruction, or specifically learned iterative reconstructions, because we use the neural network iteratively in the process. What can we actually now say theoretically in this framework? So we've written, actually now it's almost 2 years ago. Well, no, it is 2 years ago. A review on methods that come with some convergence guarantees. And the main question was first, how stable are these learned reconstructions? Which I must say, empirically, these tend to be pretty stable, at least as long as you're in distribution. And then specifically talking about these iterative methods, do those converge? Or even more, do they correspond to some variational cost function? So can we say what we are actually minimizing, if we are minimizing anything? And on top, that would be the strongest, can we say that it's a formal regularization? So regularization, we will see in a moment, means that when the noise vanishes, will we converge to something that solves the actual operator equation? In fact, at least at the time when we wrote the review, there were quite a few algorithms already out there. So keep in mind, this is from 2 years ago. So here we have actually classification between learned regularizers, where you only learn a regularizer, these iterative methods, which are actually very hard to prove anything. The post-processing, even there, people can show something, and the so-called plug-and-play framework, where you really just replace the proximal operator that we've seen before with a learned denoiser. That's actually one of the easier cases to prove. Okay, so let's have a look at some of these. What can we actually show specifically, very quickly at the end? So here we actually have now the convergent regularization. So it means in this context, we are actually only learning a regularizer. And learned or convergent regularization means that when the noise level goes to 0, so what we have here on the right, the noise level gets smaller and smaller, that we are actually converging, in fact, not to the ground truth, but something close to the ground truth, or so-called R-minimizing solution. So it needs to be a solution of the operator equation. There are a few approaches that can do this. In fact, one simple approach is actually if you just learn this regularizer to be convex. So you can use convex neural networks, for instance, and you pretty much directly can use classic regularization theory, and you get a convergent regularization. Another option is to combine this with regularization functional. So in that sense, you actually get directly connection to the classic theory with a learned regularizer from sample data. The only problem is you need to solve again the variational problem so that we know or we saw is actually slow. It could use maybe hundreds of iterations to solve this equation. So what we wanted to do is, in one of our recent works, is can we establish some convergence, specifically a convergent regularization in the learned iterative framework. And the only way that we were able to prove that or prove anything at this point is to go specifically to this plug and play framework. So when we actually then learned, we had to restrict ourselves to a learned linear denoiser. So now the proxim operator is replaced by a linear neural network, in fact, and we were able to prove that we do get, in fact, when the noise vanishes. So here we see in this graphic, the noise goes to 0 or gets smaller. We are converging to the so-called R-minimizing solution. So it's a solution of the operator equation, A or AX equals Y. But also a minimizer of the regularizer itself. So here we actually see it. It's not a perfect, but this is mostly a theoretical study anyways. So we see here, also here, we are converging down to this X dagger. Unfortunately, not the ground truth, so that's important to keep in mind. A convergent regularization doesn't tell us we're converging to the ground truth. We're just converging to this R-minimizing solution. So more information you can find in the paper, which I'm not able to cover, obviously, in 15 minutes. Good, so let's wrap up quickly. Just saying that learned reconstructions offer new opportunities by improving reconstruction qualities and reducing the computational cost. But what we need to do is we need to restrict the neural networks that we use. Typically, at least so far, this usually leads to a reduced performance simply because we are limiting the parameter space for the neural networks. But in the iterative framework, what I've presented, we at least empirically, we see that we do get quite a good generalizability, and we have flexibility to the methods or the imaging modalities we apply it to. And that's it from my side.